Welcome back to Chapter 18. We're going to look at sections H and I. So that's trig functions, inverse trig functions, and then we're also going to have a little bit of bonus material at the end. Nice. For starters, here are the 6 derivatives of the 6 trigonometric functions. All 6 of these are in the formula booklet, so you don't need to memorize any of them. That's cool. What would I like to point out here? First, there's patterns that you might notice. So sine goes to cosine, cosine goes to negative sine. Tangent goes to secant squared, cotangent goes to negative cosecant squared. Secant is secant tangent, cosecant is negative cosecant cotangent. So each of the co-functions, so like cosine and sine, there's a relationship between their derivatives. Tangent and cotangent, there's a relationship between theirs, and secant and cosecant, right? So you can see their derivatives are kind of formed in the same way. All the co-functions have a negative in front of each of their derivatives, and the regular functions do not. I'm not going to prove any of these. If you want proofs, you can look in the book, you can look online. We're not responsible for proving any derivatives in this course except for polynomials using first principles. So we're not going to focus on proofs here. That being said, I do want to just show that it makes sense. So here's a sine curve. Let's think about the slopes of its tangent lines. Right here at 0, yeah, if you told me that the slope of that line was equal to 1, I'd believe you. In fact, here's the line y equals x, and if we zoom really close in on the origin, that line and the sine function are basically the same thing. So yeah, the slope there is probably 1. As I move to the right, my slopes are positive, but they're getting less positive until right here, the slope is exactly 0. That's going to be at pi over 2. Further to the right, here my slope is about negative 1. Here my slope is 0 again, and then positive 1, and then 0, and then negative 1, and then 0. You know what that sounds like? It sounds like the y value of the cosine function. And indeed they are. The y values of the cosine are exactly the slopes of the sine function. And the slopes of the cosine function are exactly the negative y values of the sine function. But we need to be able to apply these formulas in complicated examples in conjunction with our other rules. Most notably, say it with me, children, the chain rule. Yay! Okay. This first one is x times the sine of x. No chain here, but we will have a product rule. Right? So it's going to be the derivative of x, which is 1 multiplied by sine of x, plus x times the derivative of sine of x, which is cosine of x. There we go. That's our derivative function for that one. Second one, I've got 4 times tangent squared of 3x. This one is going to require a chain rule. Again, the book's using all this u substitution. If it were me, I would simply write my answer as 4 times 2 is 8. So it's going to be 8 times tangent of 3x. So I've just used the power rule, right, because I have 4 times something squared. Then I'm going to multiply by the derivative of tangent. So the derivative of tangent is going to be secant squared. So times, ran out of space here, it'll be secant squared of 3x. But then I need to multiply by the chain rule again, double chaining here, by, need to multiply by 3 because that's the derivative of 3x. So final answer for me, I would just write it as 24, that's 8 times 3, times tangent of 3x, times secant squared of 3x. But if we want to change everything into sines and cosines, then we could certainly get from there to here. Let's just do 2 more. The co-function derivatives are far less common. Really, sine, cosine, tangent are the ones that you're going to run into the most. But so like those 3 derivatives I have memorized. Cosecant, cotangent, and secant I got to think about for a second. But again, they are in the formula book if you need them. So here, cosecant of 3x, that's pretty easy. We're just going to use the chain rule here, right? Derivative of cosecant is negative cosecant times cotangent. And we're going to fill in 3x in for both of those, and then we just multiply by whatever the derivative of 3x is, which is going to be 3. Final answer. This one here, right? This is going to be cosine, cotangent, all to the power of 1/2. So we're going to use power rule and then the chain rule. So the 1/2 comes down. It's 1/2 times cotangent of x over 2 to the negative 1/2 multiplied by the derivative of cotangent of x over 2, which is negative cosecant squared of x over 2, multiplied by chain rule again, the derivative of x over 2, which is 1/2. Final answer here. Notice in this example, the book did not use the u substitution. I'm not really sure why they decided it wasn't important here, but they did it my way, so that's cool. Great job, textbook. So that's our 6 trig functions. There's nothing else interesting to say about it. There's 6 formulas. We got to use the chain rule, the end, which brings us to section I, which talks about the inverse trig functions. The following 3 derivatives are in your data booklet. Derivative of arcsine, arccosine, and arctangent. Here's some bonus material for you. What about, the inverse reciprocal trig functions? So what about arccosecant and arcsecant and arccotangent? Those functions exist, and so do their derivatives. Here they are if you're interested. But given that those are not in the data booklet, I don't think they're ever likely to show up, and I certainly can't recall any time that they ever did. In fact, even these 3 derivatives on the left are super rare. Very, very rare in both AP and IB that you'll have to end up dealing with these particular derivatives. Now you might be wondering, hey, we've got inverse trig functions here. Those are some interesting formulas. In the last video, we looked at logarithms and exponentials, which are also inverses of each other. And the exponential function, the derivative of that was 1 over x. So that had 1 over. All 3 of these have 1 over. Is there some sort of a pattern here that has to do with inverse functions and 1 over something? And there kind of is. So this is the other bonus material that I want to share with you. So usually I shy away from doing the proofs in these videos, especially if it's something that's just in the textbook. But I do want to share with you the generalized form of the derivative of an inverse function, partially because you do need to know this for AP Calc. And actually the IB also had a question a few years back that required students to, they kind of derived this generalized formula and then they had to apply it. And it was a fairly challenging question at the time on the exam, and anytime that I've used it on exams, it's also been quite a challenge. So let's take a look at that generalized formula together. So here it is. If we take the derivative of an inverse function, that should be equal to 1 over the derivative of the original function evaluated at the inverse of it. That's a lot. Let's look at an example real quick. Well, let's use exponentials. So if my original function was e to the x, I know that the derivative of that is also e to the x, and I know that the inverse of it is ln of x. So right away, just pay attention to the notation, right? We've got the derivative of x, and we've got the inverse of x. Don't get the two of them confused. So let's pretend that I did not know what the derivative of this inverse was. We're going to try to get that using the formula up top. So the derivative of ln of x should be equal to 1 over the derivative of f of x. So that's going to be e to the, but it's not e to the x, it's going to be e to the whatever the inverse is. So it'll be e to the ln of x. And what is e to the ln of x? That's just 1 over x. Oh my gosh. That's the derivative of ln of x. Let's look at one more. We'll do arc sine. So my original function is sine. The derivative of sine is cosine. So taking the derivative of arc sine, that's going to be 1 over. The derivative of sine is cosine, so it's going to be cosine of arc sine of x. Well, what is that? Well, let's think about a right triangle. Okay, so arc sine of x, that's going to be the angle which has a sine of x. If it has a sine of x, let's talk about that angle right there. If it has a sine of x, that means that the opposite side is x and the hypotenuse is 1. If that is the case, then this third side has to be the square root of 1 minus x squared. Therefore, the cosine of that angle who has a sine of x is going to be the square root of 1 minus x squared over 1, leaving us with 1 over the square root of 1 minus x squared. Ding, ding, ding. So we can derive any of the inverse function derivatives from this formula here. And really, in AP, it becomes much more of use. There's quite a few examples of multiple choice questions that might use this as a huge shortcut. For IB, it's unlikely that you'd need to know it unless it happened to come up in a problem that walked you through it. But I think it's kind of neat, and it ties a lot of things together. So I think it's of value to discuss. Final comment here, these two derivatives came with restricted domains, so that x has to be in between -1 and +1. That's pretty evident from the formulas that we're looking at. If x were outside of those intervals, then we would be taking the square root of a negative, or if x were equal to -1 or 1, then we'd be dividing by 0. So those would be no-nos. But also recall that the functions arcsine and arccosine are also only defined from -1 to 1. There we include -1 and 1. Their derivatives, however, do not include -1 and 1, nor could they from a graphical perspective, because while I could get closer and closer to, say, x equals +1 on either of these graphs, there's no way that I could take the slope of the tangent line at exactly that endpoint, because recall that the derivative is a limit as h approaches 0, as our distance between the 2 points approaches 0. But at the endpoint, we can't take the limit from both sides. And if you think back to chapter 17, for a limit to actually exist, we need to be able to take the limit from both the left and the right. But we're really getting a little bit out of bounds here. So what do we need to know here? Really, it's these 3 formulas, and it's these 6 formulas. But again, all of which are in the data booklet. We just got to practice with them, playing with other functions, and as always, the chain rule. But that is the end of this video. Take it easy.